Hello everybody. Today we're going to start looking at another type of series, and this one is called alternating series. To get us started, let's look at a specific example of one of those series. And the series we're going to look at is the sum as n goes from 1 to infinity of -1 to the n minus 1 over n. And like we usually do, to get a feeling for what this series looks like, let's write out the first few terms of this series. So if n is equal to 1, we get our first term, and that is -1 to the 1 minus 1 over 1. And when you simplify this out, you're just getting 1. When n is equal to 2, we are getting -1 to the 2 minus 1 divided by 2, and when you simplify all of this, we have -1 to the 1. That is actually -1, so we get -1/2. So we get -1/2 as the second term. And if let's do one more, when we're looking at n equals 3, we are getting -1 to the 3 minus 1 over 3, and that is, now we have an even exponent that gives us a positive 1/3. So we get plus 1/3. And if we kept going, you can see the pattern emerging, and looking at the term in our series, the nth term, what is happening with that -1 to the n minus 1, every other term changes sign. So it goes positive, negative, positive, negative. That's the effect that -1 to the n minus 1 has. And the denominator is just whatever term we are at in our series. So we have 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and we just be going on like that. This is called an alternating series, and the alternating comes from the fact that the sign of the different terms are alternating between positive and negative. So we go positive, negative, positive, negative, and so on. Now, when you have a series like this that alternates in sign, and there are a few other things that we are going to observe about it, we can get a pretty good feeling for if it's going to converge or diverge. Over here on the right, we see some arrows, and they're going to help us visualize what is happening to this series. So that topmost arrow is an arrow that starts at 0, and it points in to the right, it's positive, and it represents +1. So let me draw in the endpoints. This is the endpoint of that top arrow that represents 1, that just represents the first term in our series. So the dot that I drew, let's call that S1, because it's really the first partial sum. It's just the first term of our series. Now let's look at what happens when we are looking at 1 and then subtract 1/2. So looking at 1 minus 1/2, that second arrow right here has length 1/2, and we are subtracting it from 1. So the tip of that second arrow tells us the value of 1 minus 1/2, and so that is the result of the second partial sum. Next, we are adding 1/3, and so we can see what the third partial sum is. And then we are subtracting 1/4, and we can see what that partial sum is. And finally, at least in our picture right here, we are adding 1/5, and so here we have S5, the fifth partial sum. So S5, I'm just going to draw that in again, that would be 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. It's our fifth partial sum. Now, if we subtracted 1/6, we would go in the other direction again, and then we would add 1/7, and we'd go back and forth and back and forth and back and forth. And if you just continue this thought experiment, where would we end up? It's a little bit hard to say where exactly we would end up, but somewhere in here. So I'm going to call that S. S is the value of this entire series. So that's what we're going to denote by S. And so we can see that, yeah, this back and forth is going to zero in on this value S. So it looks like this series converges to the value S, to this particular number. So that's one observation. The series appears to converge to a number. And in that illustration, I'm called that number S. And then every time you're adding a new term, so you're looking at the fourth term and you're adding the fifth term, and then the sixth term and then the seventh term, you seem to be jumping back and forth around this number S. That is interesting too. So we are alternating back and forth and zeroing in on this number S. So this series that you're looking at here, it has really three important properties. So first of all, it's alternating. And so alternating means it goes positive, negative, and so on. It could also go negative, positive, and so on, but in this case, it starts positive. Another thing, if you notice, the zeroing in happens because each successive term gets smaller and smaller, and the limit as n goes to infinity of 1 over n, if I just throw away the sign, I'm not looking at that -1 to the n minus 1, I'm just looking at the absolute value of those numbers, that seems to be going to 0 in our particular case. And then the third important property that this series has, if you're looking at 1, and then you're looking at 1/2, and then you're looking at 1/3, and then you're looking at 1/4, and so on, the terms are getting smaller. 1 is bigger than 1/2, 1/2 is bigger than 1/3, 1/3 is bigger than 1/4, and this keeps going on in general. So we have 1 over n eventually is bigger than the next term, which would be 1 over n plus 1. These are three important properties that this particular series has. And whenever we have a series that behaves in this way, that has these three properties, then we can generalize and look at a new test. We actually have the alternating series test. And the alternating series test says, let Bn be equal to 0 for all n, and a series of the form n goes from 1 to infinity of -1 to the n minus 1 Bn, or n goes from 1 to infinity of -1 to the n Bn, is called an alternating series. And if an alternating series satisfies the two conditions, that the limit as n goes to infinity of Bn is equal to 0, and that successive terms get smaller, so Bn plus 1 is less or equal to Bn for all n, then the series converges. So in our particular example that we looked at before, we looked at the series n goes from 1 to infinity -1 to the n minus 1 divided by n. So that was 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 and so on. So here we have Bn is equal to 1 over n. And so we already saw condition A is satisfied. The limit as n goes to infinity of 1 over n is 0. And condition B is satisfied. 1 over n plus 1 is less or equal to 1 over n. So the next term is always smaller than the previous term. And so whenever we have a series that behaves this way, then it converges using the alternating series test. There is one other important piece of information that we can tell about all alternating series, and that is we can actually estimate how close we are to the true value of an alternating series if we are just looking at the first n terms. And so that is that second theorem here, the alternating series estimation. It says if S is the sum of an alternating series that satisfies both of those conditions, A and B, in the above theorem, then the absolute value of S minus Sn is less or equal to Bn plus 1, where Sn is the sum of the first S terms in the series. So in our example, if we started with 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and we wanted to know how good is this approximation to the actual value of this alternating series, what we can say is, well, I don't know exactly what that value is, but I know I'm off by no more than whatever the next term in the series would be. And so the next term would be minus 1/6, and so I'm off by no more than 1/6. So whatever this is, this would be S5, and S5 minus S in absolute value, so S minus S5, would be less or equal to 1/6. So using the first 5 terms of my alternating series would get me to within 1/6 of the true value of the alternating series that we saw in example 1. So to complete the note, this says that if we use the first n terms to approximate the sum of the series, then the maximum error in this approximation is